Hi, I'm Aditya Behera, and this is my Physics 2211 Lab 3 video report. So in this lab, I'll be using GlowScript to find the mass of a black hole and the initial velocity vector necessary for a spaceship to slingshot around that black hole. On the screen you can see a preview of my results. Here are the physics equations we'll be using for this lab. We'll be using universal gravitation, which is the universal gravitational constant times both masses over magnitude of the r position vector cubed times the r position vector. We'll be using the momentum principle, which is just Newton's second law. Since force equals mass times acceleration, you can split it up into mass times velocity over time, which ends up just equaling dp over dt, so the change in momentum over the change in time. We'll also be using components. The parallel component of force is always along the motion of the object, and it changes the magnitude of the momentum. And the perpendicular component of the force is orthogonal to the parallel, and it changes the direction. We'll also be using the update formulas, so that's velocity final equals velocity initial plus F net over mass times delta t, and the position update formula, which is RF equals RI plus average velocity times delta t. For the first experiment, we're trying to find the mass of the black hole based off the star's motion around it. So the system will be the black hole, the surrounding is a star, and the initial conditions are the mass of the star is 2e 30 kilograms, and initial t is 0 seconds, and our delta t is 86,400 seconds, which is 1 day. Here I inputted all the initial conditions into GlowScript. This is the main calculation loop. I take the star mass and I multiply by the initial velocity to get the initial momentum, and I get the final momentum by multiplying the star mass times the final velocity. Then we get delta v and delta p by taking the velocity final minus the velocity initial and the momentum final minus the momentum initial respectively. Then I calculate dp dt, which is the delta p over delta t, so the change in momentum over the change in time. And because the net force is the exact same thing as the change in momentum over the change in time, F net equals dp dt. Then we find p hat by normalizing the momentum initial. I find the magnitude of dp dt by taking the magnitude of the final momentum and subtracting the magnitude of the initial momentum from it, and I dividing by delta t. Then I find the parallel component of dp dt by taking the magnitude of dp dt we just calculated and multiplying it by p hat. And since the parallel component of force equals the parallel component of dp dt, F net par equals dp dt par. And the perpendicular component of dp dt just equals dp dt minus dp dt par, and F net perp equals dp dt perpendicular. Then I find the mass of the black hole at that instance by taking the magnitude of the net force and multiplying it by the magnitude of the star's position squared, and dividing by gravity times the star's mass. This is just the universal gravitation formula rearranged to find one of the masses. And then I append that to an array, which I'll be using to find the average velocity later. At the top are just the print statements I do for each loop of the calculation loop, where I print the time and all the forces, magnitudes, and the mass of the black hole at that instance. At the very bottom, I calculate the average mass of the black hole by going through the array and adding them all up and dividing by the length of the array to find the average mass, and that's what I print out at the very end. This is just me running the GlowScript simulation itself. As you saw at the very end, we got a final average mass of the black hole of 8.64331 times 10 to the 33rd kilograms. For experiment 2, we're just trying to find the initial velocity vector, so the spaceship just slingshots around the black hole. So in this case, the system is the spaceship, and the surroundings of the black hole and the planet. The initial conditions are the mass of the black hole, which was just the previous mass we found. The mass of the planet is 9 times 10 to the 28th. The mass of the spaceship is 7 times 10 to the 10th. Our initial t is 0 seconds, and our delta t is 1 second. For the initial velocity vector of the spaceship, I got negative 50 e to e6, 2 e6, and 0, which, importantly, the magnitude of that is less than the speed of light. Here I just inputted the initial conditions into GlowScript. I use the general universal gravitation formula of negative g times m1 times m2 over magnitude r cubed times the r position vector to find the force of the black hole on the planet and the force of the ship on the planet. I added those together to get the net force on the planet. I did the exact same universal gravitation formula stuff for the force of the black hole on the ship and the force of the planet on the ship to find the net force on the ship by adding those two together. Then I updated the planet velocity by taking the old velocity and adding the net force on the planet, dividing by the mass of the planet and multiplying by delta t. And then I updated the position by taking the old position and adding the velocity times delta t, and I did the exact same thing with the ship, but just with the ship's force, position, and velocity. This is what the spaceship looks like slingshotting around the black hole with negative 50 e6, 2 e6, 0 initial velocity vector. So what if instead of slingshotting around the black hole, we tried to orbit it? Well, instead of having a high initial x velocity to quickly go as close as we could to the black hole, we should have a much lower initial x velocity so we can stay around the black hole. To get the spaceship to orbit the black hole, I just set the initial velocity vector from the previous code to 0, 8 million, 0. To minimize error for experiment 1, I could have let the star orbit the black hole for longer to gather more data and get a more accurate average estimate for the mass of the black hole. For experiment 2 and the what if, even though there are technically multiple correct initial velocities, since I used guess and check, there are probably better ones out there. One of the biggest takeaways from this experiment is that the rate of change in momentum, dp over dt, is the exact same as the net force. And this is very useful because it's often easier to find the rate of change in momentum than directly finding the net force. This also extends to the components as well, because the parallel net force and the perpendicular net force are the exact same as the dp dt parallel and dp dt perpendicular